Всем привет! Меня зовут Козлов Андрей. Я обсек лаборатории Касперского и также...
Hi everyone, my name is Andrey Kozlov. I do AppSec at Kaspersky, and I also run my own Telegram channel, Paintest. Some of you may be familiar with me or my work, but that's besides the point. Today I would like to discuss with you some headaches of AppSec and how this agony can sometimes be converted into bug bounty rewards. So what are we going to talk about today? Mainly I will cover DOM-based XSS. Now, what are they? Well, right off the bat, the difference between DOM-based XSS and reflected or stored XSS is that the former are executed entirely on the user's browser, from start to finish. And by this I mean that when we are dealing with a reflected or stored XSS, their execution begins with a user or a criminal sending a malicious payload to the server. And in the process of generating the reply to the user, submits or substitutes this load into the response. When this response is received by the user, by the browser, the workload is executed. A DOM-based XSS, no user data will be used by the server. The HTML is not changed or substituted. A legitimate JavaScript is returned to the user, but the criminal may force the JavaScript to use in an incorrect fashion. What do I mean? For instance, we've got some track search function that sends a request by the user, and if it contains the valid XSS structure, then it will be substituted here, and in the browser, when the script is executed, the alert will be received. And this is the most basic part of this attack, and I think that many of you are already familiar with that possibility. Why is this important? For pen testers, XSS is not perceived as a vulnerability. When I made this presentation at a different conference, people told me that XSS was not an exciting topic to discuss. But in fact, XSS is quite a basic vulnerability for pen testers. It's very interesting to compromise the infrastructure by penetrating the perimeter. But from the perspective of an OPSEC, you have to find not just one vulnerability, but instead you have to be able to find as many vulnerabilities in the target app as possible, preferably to find them all. And sometimes it's difficult to find some of the vulnerabilities because they require a lot of manual analysis of code, and DOM access is one of such vulnerabilities. In order to detect the place where it can be exploited, often you have to sieve through a lot of JS and lots of important and connected libraries to be able to find just one unsecured structure, the so-called sink. You can see some of them listed here. To understand that this structure is not exploited here. So this JS manual analysis pane will be investigated in this presentation today. So what's the gist of the problem? Say we have a website, and the website has a certain number of web pages. We are in the modern web, so all these web pages import libraries from outer sources, or they upload them from the server, or JS is contained somewhere on the website. Somewhere it makes part of the HTML. Over here you can see some unsafe structures, document write, for instance, here, and there. We know that this is a theoretical task. We know that somewhere on this website we've got a DOM-based XSS. We know that it's exploited through one of these workloads. We know that in the basic scenario, alert XSS will be used. So the task is to find where it is in order to be exploited. Since this is a modern website, it has a lot of JS. We know that manually it will be quite challenging and it will take a long time to analyze everything. That's why we start the Verpsil active scan module, so that it finds all these exploits. This is what we get after scanning. These are screenshots from one of the real-life projects. We found about 419 vulnerabilities. How many of them do you think were actually exploited? 5? That's A good guess. 3. Another good guess. 2, 2, 2, 2, 2. 0. Bingo. None of them were exploited. Why does it happen? Burp says that we've got 419 critical exploits, and that's how many we have. You will be able to find this GS. Here is the function. It can be exploited, but it's not exploited. Why is that? Well, because Burp is just like other open source. I don't know about others because I didn't test them, but open source solutions runs the analysis in the following way. It carries out the signature analysis of the website. The crawler goes through all pages, goes through all the signatures, and if he finds something that looks potentially like an XSS, he will raise a flag, raise an alert. Is it possible to exploit this vulnerability or not? The Burp will not be able to tell you that, and then you'll have to do it all manually and traverse all the 419 vulnerabilities, which doesn't sound exciting. I decided that I can't be bothered, and that's why I developed my own solution that would work the way I wanted to work. We need to find potentially vulnerable code, things in the functions, and we need to investigate whether they can be exploited. Why my own solution? Why an in-house solution? We've got Burp Suite, which has DOM Invader, which is an excellent tool. But recently, I've been very much into bug bounty, and sometimes there you get big scopes of target software, lots of websites, and if you use Burp's DOM Invader, then is going to consume all of the memory that's made available. That will go down and will just fail. It will require more and more memory. So I needed something lighter that can operate in the background to crawl through different websites, to fuzz, and to generate some alerts from time to time that it found a DOM access or that potentially it could be there. Of course, there are some open source solutions, but the ones I tested either couldn't find any DOM-based XSSs, or they couldn't find them, and they only worked with stored or reflected XSSs. But the paid solutions or paid scanners, we did not consider that because for bug bounty, it doesn't make sense to pay for very expensive solutions. Now to my solution. I thought that I would produce a pseudocode and it should be clear how it all works. Well, no, it's a joke. In fact, this is the solution. It has modular architecture. First thing we must do to collect information about GSs on the website and whether they can be exploited or not is we need to crawl through the website, all of it. I thought for a while. I wanted to devise some optimal way to traverse all of the website, not to bump into the same links several times. I decided that it's going to be a static solution, so I used Python requests. And in the first several runs, it worked beautifully. But I realized that it was not the best solution because of an experiment I set up. It was an eye-opener for me. So the idea of the experiment was as follows. I took a page from a modern website, Stack Overflow or something, or Facebook maybe even Yandex. Could be Yandex. Anyway, I requested this page statically. And then I sift through it. I wanted to find the links to collect information about the website, so I grabbed using HTML tag href. So I found 145 links, and then I uploaded the website dynamically to understand how many links it would contain. I uploaded the page in the browser, and then via the developers panel, I requested a number of pages or links, and I was surprised to find 197 links. So originally it was 145. I thought it would be different, but to be that much different, more than 35%, then I wanted to find out why this was happening. So it turns out that in the modern web, most developers delegate the process of collecting the HTML page, the final HTML page, to the server and the browser, the user browser. So basically now when you enter the website, the user gets the basic structure of the HTML page and a set of scripts. When the scripts are executed in the user browser, they call different sources, different links, they upload the data, and then they fill in this basic structure, this HTML page, with various data that they requested. So originally you have one number of elements on the page, but after it's fully uploaded, you see a dramatic increase in the number of elements on the page. Like on the Facebook, originally you will only find the scripts there and no HTML structure. That's why I decided that since that it's a bug bounty, it's an OPSEC, and they are the main task there is to find as many vulnerabilities as possible. I decided, okay, I'm going to come back to this slide later. I decided that the app is going to operate in two modes: static, based on requests, when we need to work fast without creating too much workload on the tester. And the second mode will be the Selenium one, the dynamic method. This page, if you were interested how to grab the modern applications, there's a wonderful report by Anatoly Ivanov how to capture modern web pages. Why capture? I suggest that you listen to this presentation. So you crawl through all the web pages, and everywhere you have to find the data that will be used later in our analysis. What data do I collect? First thing I gather is all kinds of all script CRS equals, and then a link. This is the construction that is used to connect libraries. We do this virtually on every page. That's why we need to understand which page uses which library. After that, I also collect constructions, script, action, script. They are JS scripts that are part of the HTML page. Third thing I collect is all events and event listeners, different templates, forms, buttons on the website. They all subscribe to different events. For instance, if we move our mouse over some component on the page, all of this is, this is considered to be an event, and there is an event listener that will respond somehow to this movement. And I also collect the JavaScript semicolon constructions, something. It's a rare case, but sometimes you do find href equals JavaScript semicolon. You still find it in practice, so it's best if you collected this data. Modern web pages are often written using frameworks. They have their own syntaxes. They use for JS and things. That's, unfortunately, I didn't have time to look into frameworks, but it's another opportunity for further development of this solution. Over here you can see why we collect all the links, all the libraries, all JS from the whole website, and after that we need to analyze it. And here you can see the main problem, why JS analysis is long and boring, and not everyone is patient enough. Because an average JS-based library looks like this. Most libraries today are supplied as bundles. A bundle is a set of code which is not necessarily used by the web application in its entirety. It may contain a lot of dead code not used at all. It's not used neither by the page nor by the application. So, first thing you do when you analyze JS is to understand which code is used by the app and which code is not used and can be killed. So differentiating between the live and dead code can also help us later for the purpose of obfuscation. In the code, you find constructions that have no meaning, but they are included there to make the algorithm more complicated or to confuse the analyzer. That's why I suggest that you do this research. So what did I come up with? To analyze the functions of the libraries, I decided that I will use abstract syntax trees. Abstract syntax tree, an AST, is a structure that enables to take a code or a program and represent it as a tree. The leaves would be variables or function returned or a constant, and the apexes are the actions, summing or deduction or something else. Why is this useful? Why it may be useful? Sorry about that. Why is this useful, or how it can be useful? ASTs enable static analysis without emulating the user browser. So basically, you can take an AST as is and crawl along all branches and see which fragments of the code or functions will be executed under which circumstances, which is a great advantage over burp. Burp monitors the execution flow. It opens the page and makes actions to see how the function is called. And it investigates only the parts of the code that are executed at that moment. So if a certain condition is not met, then that part of the code will not be investigated. But we want to understand all of the code to find all possible vulnerabilities, and then we'll be able to understand which workload will be able to call which vulnerability, while ASTs allow us to see possible outputs of all functions. In other words, what does my solution do at the current stage? You collect all GSs, all functions, and then you start analyzing for each of the functions. You build an AST. But the way you do it is you take the researched function, you build its AST, and if you find a nested function that is called from it, then you build an AST for the nested function and you connect it to the main tree. As a result, you get a huge AST that will reflect all of the actions and all possible types of events when users press a certain button. Why is this useful? First thing, we only keep the functions that are used by the app. All others are not considered. We will be reconstructing only the functions that are contained indeed in the web pages of the site. And it enables quick analysis. And we'll be able to find unsecured sinks in the tree. We move along the tree to find the unsafe constructions. If we find such an unsafe construction on the tree, we'll see that potentially it's a vulnerability and it will be isolated. If we couldn't find a sink, like on tree number 4 over here, probably you can see it, we understand that it's it's not a vulnerable sink. If there are no such constructions, then the tree, this function, will be isolated in a different place. It's fully secured. We don't need to come back to it. What do we do with the remaining functions? Like here, we had 4 parts of the tree, 4 functions. 3 will be analyzed further. And 1, we have already proven that it's safe. At this stage, having performed these steps to collect GSs and conducted the primary analysis, we identified 3 groups of code or functions. Dead code is wonderful for deobfuscation because we do not need to consider it. We don't need to analyze it. Then the parts of the code where we found unsecured sinks, and these will be analyzed further. And the third category are the secured parts of the code where sinks are not found. In terms of subsequent analysis, we detected the functions that are potentially vulnerable. So one last question to be answered: are they really vulnerable or not? So we need to test the fragments of the code that are potentially unsecured and can lead to the DOM XSS exploitation. So here is my idea. I take a function. I know that it contains an unsecured sink. I just need to understand whether it's reachable. And then I need to understand whether this function calls any regional variables, or it calls any global variables, any sources. If yes, for instance, our function takes some variables as input, then I will set a value, like a validate to this variable. Then I follow the AST and I perform all the necessary transformations. If in the unsecured sink I see the same variable, I know it's used there, then this is a guaranteed proof that it contains DOM XSS, and I return a report to the user. If I run this function several times and with different input values, and I see that the results differ, then I know that the input somehow affects the output, but it's not a direct impact. But we need to connect to the user to be able to analyze the mode of this impact. Or sometimes I will see that the input doesn't affect the output. The output is always the same, regardless the value at the input. Then I will say that this function is secured, it's safe, and it doesn't contain any DOM XSS. So basically, that's it. So at this stage, we found the parts of the code that were confirmed to contain DOM XSS. We know that there is a set of code that requires further investigation by the user, but that's just part of all the studied JS in this web application. And the third category of our findings are extra functions that we can't exploit. Now the big question. In theory, it all works fine, just wonderfully. What about practice? It's great that in the last several years in Russia we acquired several bug bounty platforms. I reported one of them regularly. Bug bounty platforms allow us to test our own hypotheses and solutions. Here are my results. They show that this solution is viable. It can detect vulnerabilities and it can generate some money. It can operate in the background mode. You can run it for a week, forget about it, then read through the reports and report your findings. What are my subsequent steps? Well, first of all, I'm going to develop this solution further. I want to integrate it with various frameworks. Like I was saying, many modern websites are using frameworks. So it would be interesting to analyze them dynamically. Unfortunately, I just didn't have time to make that product. Since the architecture is modular, often you have to find endpoints that are embedded in the JS and that are called from the user browser, or to find endpoints or to find secrets. Sometimes I see that, say, there are keys, tokens, logins in the JS, and you can basically develop an extra module that will find this data during the analysis. And thirdly, since we analyze the code and we select which code is dead and is not used by the application, we will be able to employ this information for deobfuscation purposes. It's just an idea. I don't know how it's going to be implemented. Maybe I'll make a presentation at one of the later conferences. Thank you. That's it from me. I'm ready to take your questions now. Hi, and thank you for the presentation. I have several questions. I don't know if I'm allowed to find them all for all. Yeah, the first question is on validation, because you said it was the last step in the process. So you detect a function, we think it may be a vulnerability, and you mentioned that the variable can be assigned a validate value, and then we'll be able to test whether it arrives at the sink or not. Then how do you do it? Is this a static interpreter for AST, or you do it dynamically somehow? Can you go into details? How does it work? How do you set the value of the variable? Well, at the moment, it's static. I have an AST. It's an array. It's passed. And I look at the values at the input. I know how it looked, the function, how it looked at the input, and I know where it is in the AST. If I see that this variable is used somehow in the AST through scanning, through crawling, then I will change its value to the one that I'm showing here. And after that, I will follow it through to the sink to see whether this value affects anything. So is your role in the interpreter for AST JavaScript? Well, yeah, you can put it this way. Another question. In the beginning, you also mentioned that you determine functions that have sinks, and you said something like you take the function and the nested functions that are called from it. Can you please explain what you mean by nested and called? It means a function that are defined inside it, or they are the ones that called. But it's difficult to do it in the JavaScript. How can you determine which functions are called from another function? Well, I analyze the code, and if I see that within the area of visibility I have another function that's been called there inside the same library, say, then I follow it, and I build an AST for it. And then I connect the new AST to the old AST. But how can you find this function? That's my question. I mean, how do you find it in the area of visibility? I mean, this graph is very difficult to build. It's almost impossible. What's your solution? Well, in general terms, yes, it's difficult to do, but at the moment I do it in a very straightforward fashion. After that, we can go deeper into math to build the graphs, but right now I just do it directly. I take the same library, I scan it, I find the same construction. You mean the name? You just search for the name. Oh, okay, I got it. And the last question. Well, maybe not a question really, but a request. You said that you build a page in the browser, and after that you parse it to find all the links, and then you parse it, and there you find the scripts, right? But look, wouldn't it be better, have you thought about it, wouldn't it be better to use the browser debugger to understand which scripts are dynamic? And then everything that you found, because you said you had to do it manually to parse everything, to parse the attributes. So if you would use the browser debugger, you would be getting the same information, but also the ones that are dynamically uploaded. Maybe there's a bundler. It's a bundle, right? Part of it is uploaded immediately, and part uploaded dynamically. Yeah, it's a cool idea, actually. I should be thinking about that. In our analyzer, that's what we do. We recommend this approach. You do it for the HTTP endpoint mining? Oh, I enjoyed your presentation so much. Right, and the last request. You also said you had findings at Bug Bounty. Can you show us the code, a bit of it at least? What did you analyze to find the bug? It would be better. I mean, I think it would be more visible and easier to understand. Oh, wonderful questions. Thank you so much. Hi. Do you plan to make your developments public? Well, yes. wanted to make it available to the whole community, but several days ahead of the conference, I decided to refactor it, and the consequences were dire. Here is the link, right? You can write to me, and I'm going to polish it in the next couple of weeks. I'm going to publish it. I'll make it look beautiful first, but yes, I plan to publish it. You can write to me. You can write me to my Telegram account. Hi, thank you for the presentation. DevTools, yes, you took the other guy took it off my tongue, but I wanted to ask you about something else, obfuscation that you have to overcome at the initial stage. One of the simplest options when you have a lot of that code in the bundle. But my question is, in the process of running your tool, have you come across more complex cases of obfuscation? No, not yet. Do you have any plans? Yes, I would be happy to. Because it's the ping substitutes, XM substitutes, there is a whole set of complications ahead. Let's get in touch because I have a lot of ideas how we can test your tool with more complex cases. Okay, thank you everyone. Thanks for your attention. Oh. Sorry. Last thing, people ask me, we are Kaspersky Labs and we are looking for more people. Everyone's welcome to apply.